Okay. Okay. So we have a few interns here, a few new interns joining us here at Pangolin. We have one from USC and we have one from Dartmouth. And I wanted to kind of bring them up to speed with what's so special about laser and give them a history lesson about Pangolin laser because they work in the field of video, such as Unreal Engine and things like that. 3D meshes, machine vision, computer vision, that sort of thing. And so it's a very far from laser to your normal computer graphics. So I'm going to be giving a little bit of a presentation here to bring them up to speed, and figured that they're not going to be our last interns. And so we'll just make this video here, and it could be of general interest as well. So I figured we'd just have we'll just film it all and go like that. So here we go. Welcome to Pangolin, our new interns. And let's see, I'm going to start off with a kind of origin story of how Pangolin got started. And I'm going to start with Papa John's Pizza. I hope don't make anybody hungry. But if you go into a Papa John's Pizza, you're going to see something that looks like this. A little poster on the wall that tells you Papa John's own origin story. It says, "I traded my wheels for my pizza peels." And it is a story where Papa John Schnatter sold his prize Camaro in order to get enough money to start a pizza delivery service in his dad's tavern. And he started this pizza delivery service in the broom closet of his dad's tavern. That was the beginning of Papa John's Pizza. And so, in a similar way, my story begins with a guitar just like this. It's a 1983 Strat. This is not a Stratocaster. This is a Strat. And to prove it, go ahead and zoom way in on there, and you'll see this is the Strat. In the early 80s, Fender was going through a kind of rejiggering. They wanted to reinvigorate the brand. And so one of the ways that they did this is one of the ideas they came up with, was the Strat. It's a Stratocaster, but it's made in a little bit of a special way. The headstock here is painted, as you can see, which is pretty unusual. The way that the logo is kind of impressed on there is kind of unusual. All the hardware is gold plated with a very heavy gold plating. And finally, the thing that makes this really special is that ordinarily this would be a tone knob, and that's not the case. On this guitar, it is a 2-position switch, and you have your 5-position selector here, which selects between the pickups. And what this 2-position switch does is gives you additional ways in which the pickups can be connected and configured. So this can give you 9 separate sounds instead of just the 5. And so why am I holding this guitar? Well, like Papa John Schnatter, who sold his prized Camaro to get enough money to start Papa John's Pizza, I sold a 1983 Strat, looked just like this, in order to get enough money to buy a laser. Because in the early 80s, I was in a rock band. I played bass and synthesizer. I bought a guitar too, mostly just to amuse myself, but I played bass and synthesizer in a rock band. And we played top 40s music and that sort of thing. We played at birthday parties and college getaways and that sort of thing. And in our band, I made all of our lighting equipment. And so we didn't have American DJ. There was no .coms or anything else. Now you could just go to American DJ and get whatever you want, and it's cheap and it's plentiful. Well, in 1983 and 4, there was none of this. And so I had to make up our own lighting things. So you might have heard of par cans. Well, I had soup cans. Literally took incandescent light bulbs and put it in soup cans and grapefruit juice cans and that sort of thing, and we could get some theatrical lighting gels, put it over this thing, and it put it all together with PVC pipe and wood. And I made a lighting control desk, and it wasn't even out of 7,400 series logic or microprocessors. I made this thing with transistors and diodes and that sort of thing, but nevertheless was able to create our own lighting board, which was intelligent enough to listen to the music and sequence the lights. And so I had a lighting system for our band. And so I was inspired by the laser shows at the time that were being put on at concerts from Blue Oyster Cult and Pink Floyd. So inspired by that, I said, well, we need a laser for our band. Let me look into this. And what I found was lasers were big, expensive, really unobtainium. Nevertheless, I was able to find a company called Melis Griot, and I, with the money that I sold my 1983 Strat for, I bought a Melis Griot 5 milliwatt laser with a 12 volt power supply, and here is the actual receipt for it. And what we can see here is that it is dated June 23rd, 1986. So when I tell people I've been doing this nearly 40 years, I'm not kidding. I literally have the receipts to prove it. And so, so I had my 5 milliwatt Heaney laser there, and got the laser. Now, today, if you say to somebody, I bought a laser, what they really mean is I bought a laser-based product, right? I bought a whole laser system. What I'm talking about when I say I bought a laser, we'll have this be the stand-in for the Heaney laser. It's literally, you get a laser. It produces a beam of light. Congratulations, you've got a beam of light. Now, what are you going to do with it? Okay, so the first thing you do when you get a laser is look at the beam. All right, now I had a girlfriend who had a house on the beach at the time, and so what we could do is we can go out at night where it's dark, we have salt air, mist in the air, great place to look at a laser. And so what we do is you turn on the laser, you point it down at the ocean where there's nobody there, and what you could do is you could look at the beam. Look down there, you see the beam? Now what's interesting is this, when you look at the beam from here and you look down it, the beam is very small. You can see how small it is, 1 millimeter nominal. And from this perspective, it seems like it keeps that 1 millimeter size forever. It just looks like it keeps going and going and going, and it keeps that 1 millimeter size. But what we found was I put the laser on like a little desk, and we can go down to the beach and we could look at the beam from the water, the beam sitting up there on the table. And what you see is that now the beam is this big, and you could actually look into the beam and you walk around the beam. It's like, wow, this is amazing. And so what you get to learn about is divergence. From this side, it looks infinitely small and it stays infinitely small, but when you look back on it, you get to understand the beam has divergence. So this is kind of like lesson number 1. So that's what you do. You look at the beam. But eventually, looking at the beam, you get to learn about divergence. This gets boring after a while. Plus, the beam itself is not a laser show. So the next thing you do is point the beam at things. This is step number 2, right? Point the beam at what? Well, what you have is stop signs and traffic signs, like speed limit 15 miles an hour, that sort of thing. Now, what's amazing, and I can't demonstrate that here, when you shine a laser at a speed limit sign or a stop sign, it all of a sudden glows like crazy. It is amazing. It's just the whole thing just explodes with light. And so I said, well, hey, here's a car. What I'm going to do is I'm going to wait till the car gets close to the stop sign. I'm going to illuminate the stop sign with this laser pointer, or this laser, and the car is just going to freak out because the stop sign it suddenly gets super bright, right? And they do it, and the car doesn't freak out. Oh, here comes another car. Here's a speed limit sign. Here, we'll hit the speed limit sign, and we'll really freak the car out. And you shine it at the speed limit sign, and the car goes by as though nothing happened. So you say, here, you hold the laser. I'm going to walk over here in the street and take a look at what the person's seeing, and what you see is virtually nothing, because these stop signs and these speed limit signs and that sort of thing are coated with something called 3M high reflectivity material, which sends the light back towards you. Great for stop signs and traffic signs and that sort of thing, because you got the car headlights, you want to illuminate the sign, you want to send all that light back to the driver, so this is what they see. But when you're off axis, you don't see it, because the light's going back towards the laser, you're off axis, you don't see anything. You might see a dim red dot, not enough to make cars freak out. So the next thing maybe you have in pets, you're doing this with the pet, doing this and the cat freak out. At least the cat will freak out. Drivers won't freak out, the cat freaks out, you're doing this, chasing the cat around. And what's funny is you could do something like this, you got there, and the cat, he puts his paws on top, and at the moment he puts his paws on top, you turn the light off, and he picks his paw up and the light's gone. He's wondering what happened to it. So, yeah. But eventually, this gets boring. Plus, it's not a laser show. Even the cat gets bored by it. So the next thing is to shine the laser through things. So first we're looking at the beam, then we're shining the beam at something. Now we're going to shine the beam through something. Through what? Okay, so I have this little thing of water here, this little vessel of water. In my case, it was a fish tank. You can put the beam here, shine the beam here. What you can see on the black curtain, you can see since I've got a round thing here, you could all of a sudden now what we've created is a cylinder lens. You'd also shine the light down into the water, and something amazing is going to happen. As I make the beam more and more and more horizontal, the beam keeps bending into the water. And you see the beam is really going down into the water, even though the laser is now almost completely horizontal. When the laser hits the surface of the water, it will bend down into the water. So you say, oh, that's interesting. You get to learn about diffraction. So we get to learn about divergence. You get to learn about refraction, rather. And now, let's see. We're going to walk around the house and pick things up and start shining the laser through stuff, such as your mom's diamond ring, right? And you just kind of pick it up and shine it through. What does this do? Okay, well, this kind of does something interesting, but mostly not. So, okay, you go down to the next household thing. Eventually running into shower door glass. Now, here's the funny thing. A lot of this, as I thought about this presentation, thought about how I was a kid and what things were like when I was a kid and how different things are now. This is a theme throughout this whole presentation. So back then, we had shower door glass, okay, because we had people who had modesty. Now all the shower doors are regular old glass. So if I say shower door glass, people are just thinking, well, it's just glass. But when I was a kid, the shower doors, you couldn't look through them. They weren't just regular glass, they were textured glass, right? So you could shine the laser through this textured glass, and all of a sudden now you have something that could be interesting. It creates all these refraction type things, and you can move the laser through this. So this is what shower door glass does, and I've got a couple of samples of shower door glass here. This is one of them. Here's another type of shower door glass, or glass that you might find in a house or shower door, and you just, when we shine this thing through, you can see that it just kind of creates these patterns and kind of smears the light around in very interesting ways. And this is known in the industry as lumia. That's what this effect is called. My friend Doug McCullough, who I call the Steven Spielberg of laser show, he says lumia is to light what music is to sound. So I've got a couple more pieces of textured glass here to show you. Let's see. Maybe come up here. So you can see it just makes these interesting patterns, and each of the different types of shower door glass will make different types of patterns. And some people in the early days of laser shows, this was one of the effects that they did. This is a kind of a staple. They would shine the beam through and have this rotating. That's why this thing is round and it has a hub on it. They would put this on a motor, slowly turning, and then you'd have this lumia. We call this a lumia projector. And also, back in the 80s, when I first got in, you could buy diffraction gratings from a company called Rosco. They made the gels, like theatrical gels, that you like, the red and green and yellow and magenta and that sort of thing, what we call gels, the colored plastic you put in front of lights. Back before we had moving light fixtures, you change the color. This is how you do it. You put a piece of plastic in front of a light bulb. Congratulations, there's your colored light. So, but Rosco also sold diffraction gratings. And this is like the only thing where something in the 80s was cheap and plentiful, and now it's scarce and expensive, which is diffraction grating. You can go down to Rosco and you could buy large sheets of diffraction grating, super cheap. They were available and Rosco stopped selling them. But I'll show you what a diffraction grating is, or what it can do to a laser. You got our laser beam, you shine the laser through the diffraction grating, and what it does is it can break up the beam into many small beams. And so now what you could do, and what some people have done, is you put this on a motor and it can rotate around and that sort of thing. And I think I've got another type of diffraction grating here. Yeah, something called a Machida grating. It's a different type of grating where you shine a laser through it and it will create a line, basically a line of dots. And I have it in the case here. It's normally really cool, it's normally a lot cooler, but I don't want to take it out of the case. So a diffraction grating can break up the beam into many different little beamlets. So what we've done, and you get to learn about diffraction. So we learn about divergence, we learn about refraction, learn about diffraction. This could be a laser show. Some people did it in 70s and 80s. But eventually you get bored with this. And you come to a place where you need to do the next big thing. And the next big thing is to scan the beam. All right, so when I mean scan the beam is you got the beam. I'm going to just move it around with my arm. If I move it horizontally, now I'm scanning the beam. If I move it vertically, scanning the beam vertically, I can move my hand round and round, and now I can make a circle, right? And I could wiggle it faster and faster, and that sort of thing. So this is scanning the beam, in other words, moving it. Now at the time I worked in the very early 80s at a television shop, and televisions, they had these things called tubes. They had a CRT, right? It was a cathode ray tube. It had an electron gun in the back, and you had something called a deflection yoke, and you can move this electron beam, and the electron beam would strike a phosphor target and light up. And that's how television worked. Television had XY scanning, vertical and horizontal scanning. Now, they were able to use magnetism, and in my experiments I discovered that you can't use magnetism to deflect the laser beam, so that leaves mirrors. So I've got a set of scanners right here. And so what I was able to do is actually make my own scanners. I won't exactly say how I did it, but it was kind of sophisticated, not as sophisticated as our scanners today. And so what we could do here with these two motors with mirrors, we have a laser, we can shine the beam through here, and we can move one mirror and make the beam move vertically, and we can move the other mirror and make the beam move horizontally. And now, by using these motors with mirrors, we have XY scanning. And you might get the feeling that you could do a whole lot more with this, and it's going to be a while before you get bored, as long as you figure out how to drive these things. So you have motors with mirrors. It's a good news, bad news situation. The good news is that almost all of the light gets through because it's a mirror, it reflects off the mirror. And also another good thing about it is that if you have multicolor laser, since you're moving mirrors, it will reflect all of these colors by the same amount and at the same time. so you can use scanners to reflect multicolor laser beams. The bad news is that you're actually moving the mirror. It's a physical mirror, right? It has weight, it has mass. And as you start to move it faster and faster and faster, it just becomes harder. It takes more mechanical power to move that mirror faster and faster and faster. And there's another thing too, which is these mirrors look solid. I can ting them with my fingernail. They are solid, but at certain frequencies, the mirrors will start to resonate, and this resonance could actually distort the projected image, right? So it's, like I say, it's good news, bad news situation with laser scanners. Nevertheless, okay, so we've got our XY scanners. So what are we going to do with them? So the next evolutionary step, after I was able to get my laser, put it on a set of scanners, now we have to drive the scanners. So the very first thing that I did was to make analog oscillators, and I'll show you what that looks like up here. We have a laser projector here with XY scanners, and I'm going to show you what it looks like when you have, this is what we call a quadrature sine wave. A sine wave goes up and down, right? For example, what I'm going to do is make this 0, and we'll make this 1 hertz. So this is a sine wave going on the x-axis, right? And I can put another sine wave on the y-axis here at twice the frequency. And so now we are moving the beam. We have an oscillator for the x and an oscillator for the y. We're able to create shapes, in this case very slow. I'll speed this up to what's more normal. We got 30 hertz there on the x-axis, and let's say we put 60 hertz on the y-axis, and we have a pattern that when I first saw it, I called this Spider-Man. I don't know why I called it Spider-Man, but every time I see this pattern, I say, that's Spider-Man. So then we can change the frequency here, get this here. If the frequency relationship is not exact, what will happen is you get what we call phasing. This kind of phasing type of situation. So let me put this back to the same frequency and restore when you have two sine waves going the same frequency but 90 degrees apart, it's what we call a quadrature sine wave. So now what we could do is, again, I worked in the television shop. The newest televisions at the time, the volume controls worked off of a voltage control. It wasn't just a simple pot. And so I knew that there were television sets that had voltage controlled volume. And so therefore I thought we can use this as an amplitude modulator. And so we took these chips, this volume controlled chip, and turned it into an amplitude modulator. So you could take another sine wave, let's say 120 hertz, and amplitude modulate means that we're going to take the original circle and make it smaller, change the amplitude of it. While it's scanning, I'm changing the amplitude. So that's what we have right now. We have amplitude modulation. So we have our circle going around 30 times per second, and we have 120 hertz amplitude modulation, and this is what it looks like. And once again, this is 121 hertz. So now we have a phasing amplitude modulation type appearance. We can continue to, and another thing we could do is change the waveform. Up until now, I've shown you simple sine waves, so I could change the amplitude modulation to a triangle wave. It makes the pattern look kind of pointed on the ends and kind of like a flower. We could use square wave instead of a sine wave for the amplitude modulation. And this is the kind of pattern it makes. And once again, you change the frequency, And then, if you want to get really advanced, we could put what we call blanking on this, right? Blanking means we could turn the beam on and off, like this. So now, let's say I'm blanking the beam 120 times per second, and so basically I'm turning the beam on and off 120 times per second while it's scanning and amplitude modulating. And we can get faster and faster and faster here. And then later on, once I was able to get into colored laser projectors, you can do something like this here, where we have colors. Maybe I go 30.1 hertz. So by this blanking thing, you can make it have a tracing appearance. So let's review what I've actually created here. So I've got this laser that can be powered by 12 volts, such as a motorcycle battery or an alarm battery for an alarm backup battery. I have created analog oscillators, and scanners, which can move the beam horizontal and vertical. Everything here is in the audio frequency range. All right, so now, and I can turn these knobs, and because it's in the audio domain, I can record it on cassette tape. We had these things called cassette tapes. They were about this big, right? I could record a laser show, which is really just audio, on a cassette tape. Now, I could take this cassette tape and put it into a car stereo cassette player, which runs on 12 volts, and has a power amplifier in there, which normally runs speakers, but we can make that power amplifier run scanners. So what I've got is a portable laser show. It could be 12 volts. You can literally carry it anywhere, and pretty portable. You got the battery, which is about the same size of a car radio. You got a car radio, and you got some scanners and a laser. Everything runs on 12 volts. So now we have a portable laser show, just like Pink Floyd. No, just kidding. So what we did was, there was a particular song in my band that came up, and my girlfriend strung this sheet, literally a bed sheet, which rolled up and tied it with little bows on the end, and had this little kind of thing where if you pulled the string, the bows would release and the sheet would roll down, revealing the sheet. And so there was a particular song towards the end of our set where she would pull the string and activate the 12 volts, which would start the car stereo player with analog abstracts on it and the 12 volt powered lasers, and we can have a laser show. And since I made the lighting board, we literally cut the lights. And even though it was 5 milliwatts, if you're talking about a beam, remember, the great thing about lasers, let me tell you one more great thing about lasers. It's a beam, right? All of the power is right there. Now, if we start scanning a circle, we've only put the power where the circle is. Now, under ordinary circumstances with normal projection means, what you do is you put the light everywhere, whether you want it or not. You put the light everywhere, and you only turn it on where you want it, right? And this would make the thing very dim. If I was to take this and put it through a lens sufficient to cover the screen, it would be a very dim green thing. You might not even see it. But since it's a beam, and we're only going to put the beam where we want it, you can have a lot of power. This is a kind of efficiency type deal, right? So this worked as our laser show. So what happened with the band? What happened with many bands? Nick, our drummer, moved up to Jacksonville, Florida to start a business with his two brothers, very successful business. I lost track of the guitarist, Bob, leaving only me. And so I did laser shows for a few other bands. I became kind of, the laser show did get our band noticed, and we became known for, hey, we were the only ones except for Pink Floyd and Blue Oyster Cult at a laser show. So I did it for a couple other bands, but that was kind of the end of it. So, but nevertheless, eventually, the abstract shows become boring. Now, before we get there, what I'm going to do is we will play a show for you, an abstract show, so that you could see what the best person, one of the best people who does abstract shows, what they can do with oscillators and that sort of thing. I'll play that show right now. So you could press pause, Dan, or stop.